Yeah, so as folks are filtering in, I thought that we just start out a little bit this morning talking about, just what are real world examples of models that work and models that don't work. And, just thinking about this, not necessarily from the very specific perspective that we talked about last class, but just more generally. So I'll give one of my favorite examples, and then David will chime in with examples as well. So in terms of models, I think a really good example is the use of the Gaussian copula in mortgage risk forecasting. It's like the 2008 financial mortgage crisis, which I realize to some extent is becoming an increasingly dated example. For me, it was it was a big deal, right? Because it was like while I was in grad school, and I was like, I am so glad that I have my grad school salary and my grad school job right now. But so in this case, like simplifying down the zillion factors that were going into this, in this particular case, there was an assumption made about how risks are correlated with each other, right? So at the core, or at least the core of what I'm going to explain in terms of, I think at the level of 181, is this assumption that if one person fails to repay a loan, that's independent of another person failing to repay a loan, or not completely independent, but not super correlated with each other. And this turns out not to be the case, because maybe there's a factor that goes around, like affects multiple people at the same time. If there's a crisis in a particular region, maybe many people are losing their jobs at the same time, and now are unable to, all of those people are going to be unable to repay their loans. I mean, you think about the pandemic now, right? Lots of people are having trouble with paying their mortgages and their rents and stuff like this, and it's not an independent coin flip, right? There's something going on underneath.
Correlated risk.
Exactly. And if you model your risks, assuming that your risks are not correlated or not particularly correlated, the model will optimize and it'll tell you what to do. And it will give you some decisions that don't make a lot of sense, right, when you actually put them out in the real world. So I think this is an example of a model that, I mean, the math was all correct, right? People churned through it.
But the math was correct, but the model was wrong.
Exactly. Yeah.
And then people made decisions on the basis of that, and they got in considerable jeopardy.
Exactly. And you wouldn't have noticed this by just going line by line through your code.
Right.
This was
I have another example that I like of models gone wrong. This was a digital marketing example where I was helping a company that tries to find neighborhood offers. So offers for merchants, let's say in a local neighborhood, to help one merchant introduce its favorite customers to another merchant. And we trained what we considered to be a beautiful model. I'll tell you what it was in a second. We had features of consumers, we had features of offers, and we started working with this. And one day somebody said, the model is predicting the same preferred offer to every consumer.
Okay.
So, well, that seems problematic, right? So
yes.
you've picked a model, and you want to be finding the idiosyncratic things. What is it that Finale likes about things she might want to buy around her? And we took a step back and we realized that the problem was that we were using a linear model, and the linear model had no interactions between the consumer features and the merchant features. And because it had no interaction terms, it was a logistic regression model. User features were coming in as basically upward shifting the likelihood that any one user would convert on an offer, but was not changing the shape of the curve across offers. So the peak of the curve for you was the same as the peak of the curve for me. It's like, this is the right offer, offer 8. Everybody should prefer offer 8. And so we picked the wrong model because we hadn't correctly understood the nuances of the problem we were working on. And we should have been using something like random forests, which is what we then adopted.
Over to.
Yeah.
Well, that reminds me of something that actually happened in our group, where the kind of the opposite problem, where I guess we overfit. We had a model and we assumed that in these data, the right antidepressant for a particular patient would depend on patient features, and hopefully the antidepressant is going to affect the outcome, right? So antidepressant and patient features produce the outcome, and you think that there should be some interaction, right? Because there's a right drug for this person,
right?
And once we did it, and it seemed to find, it looks like there's certain drugs that work better for certain people, or it was predicting drugs, and those predictions were working out well. And then we realized that we had basically overfit. And in the data that we had, the strongest signal was really, there are some patients who are likely to get better just because their illness is not so severe, or it's more treatable, and they're probably going to get better regardless of what treatment you give them. They have an easier version of the disease. And then there's other patients who are just going to be hard to treat. And we were so focused on finding that interaction term that we did not, because there's some collinearity, right, or joint dependencies. We didn't initially try to just check to see, wait, how much of this is dependent on just the qualities of the patient and not the drug at all.
There you were overfitting to interaction effects that were actually not something that would generalize to a new user population.
Exactly.
Yeah.
Or in a way, it kind of would, in the sense that I think if you use this model, you would realize that you would recommend a drug to that patient, and they would probably get well. But it's not because you chose the right drug. It's because that was an easy patient to treat.
Getting better anyway. Fascinating.
Cool. All right. So I'm going to switch over to sharing my screen, and we are going to talk about model selection part 2. All right. So here is where we are, folks. Over the first initial set of lectures, we went through the supervised part of this cube, continuous wise, discrete outputs, probabilistic, non-probabilistic. We looked at all those different options. And now we're in a phase of deepening our understanding of those models. So right now, today is day 2 of 2 for model selection, and then we'll have mini segments on more expressive models or deep networks, and more fancy losses. And just in terms of logistics, homework 2 is due on Friday. Okay, so what we're going to be doing today is this is going to be one lecture, basically, on the gospel of Bayes, right? If you're Bayesian, there's one way you solve a problem. It's very mathematically elegant, but it also does have some limitations, because there's kind of just one way of doing things, and sometimes it's easy and more often it's very hard. But anyway, I'm going to give you basically this viewpoint. I'm going to say from the beginning that, and those of you who were logging in early on may have heard David and I chatting, that this is not something that I think of like as you're going to practically go out and use in the real world once you've seen it here. But I do think it gives you a very useful conceptual framework on how to think about an alternate view of model selection, first of all. And second of all, there is some beautiful math, right? Maybe I'm biased because this is the area that I work in, but I do think that there's some beautiful math, and it's nice to enjoy some beautiful math sometimes. So that's what we got for today. So today, again, Bayesian view on model selection. So what we're going to do, first of all, is expand how we think about generative models to describe the Bayesian viewpoint. So currently, in our models, we have our X's in our supervised learning problems, and for most part, they are producing Y's. So our story is that there's some input X, we sample Oh, right. So David's making a useful point. It's like, have we done y produces x? So that's a really good point to make. So when we talked about classification, we talked about discriminative models and generative models. So let me just, I think this is a little bit of a diversion, but let me just point that out. So we had the models that went from x to produce y. These were our discriminative models, and in these models we were modeling p of y given x. And then we had our what somewhat over, put this on the side. I'm overloading the term generative because I've been using generative as just in general for like the generative story over here, or generative process. But the generative models had this assumption that the y produced the x's, and we ended up modeling this joint distribution. And both of these can make sense in different scenarios where you can think that, okay, I have some inputs, like I have some features about this customer. I want to know, this is my customer features, and this is like what they're going to buy, the product that they're going to buy. In a lot of other cases, it might make sense to think of it the other way around, that, this is the disease that the person has, and these are the measurements of the disease, right? This is the person's temperature or something like that, right? So both of these are possible. For now, for today, we're going to go with the story that there's some x's, and the x's are producing some y's by, we sampled some noise, and then we said that, for example, y is equal to w transpose x plus epsilon. So that was the linear regression case that we talked about, right? So this is what we did. And now I'm going to make the story a little more complicated. So I'm going to add a step 0 to this story. And step 0 actually is, so there's this picture that I drew here has one part that I never really made explicit, and that's this w, right? But the w matters, right? The w is right here. It's helping produce the y that's coming out. So now I'm going to think about this w more explicitly, and I'm going to say that w is drawn from some prior over w, and then this process repeats itself, n times to create our data set. So the main thing that I've changed about the story is that instead of w being a fixed parameter, w is now a random variable. That's the key difference that we have now. All right, so now that w is a random variable, so let me just write that down. W is a random variable. There are a couple of things that we can do. And if you're Bayesian or using, then there's really only one way to solve these problems, right? This is where, the Bayesian viewpoint is both a very elegant, but can, in some ways restrictive, because it tells you there's only one way to do this. But we can do a couple of things. So given data, we can compute the posterior P of W given the data, right? So there was some prior that we had over the W's, that we believe that the W is drawn from some distribution, and then you collected the data set. Well, now once you've seen the data set, you can compute this posterior that says, what's the probability distribution over W now? Now that I've observed some data, what is the new distribution? And we'll expand this in just a few moments as we go through lecture. Another thing we can do is we can compute something that's called the posterior predictive. And oftentimes this is the quantity that we really care about. So we can compute the probability of y at some new locations. I'm going to use the little, well, or maybe I'll just try. I'm going to try All right, what's going to be best for me? I'm going to put this to mean like at some notation that's at some location that's not in your training set, a new test point. So if I want to compute the probability of y at some location x, given the data that's already been collected, so this is your training data. Let's just be really clear. And this is your test, your new location that you're interested in. So these are your, you're trying to make a prediction for this, this particular x over here. We can write this down via the following integral, right? There's a very specific way we can solve this, or we can think about what are the possible w's. So the probability of y given w and x times the probability of this posterior. We're using lowercase. Posterior over the possible w's, dw. So what we're doing here is we're integrating over all the possible w's. So we have a distribution over possible w's, and for every possible w, we're going to have a situation, or we're going to have a distribution over y. So just to draw this out in pictures, let's say that we had some training points like this. We're trying to make a prediction at this location, x prime. Well, the way this integral is breaking this down is saying that one possible w could be this one. So if this was w, then we're going to have this distribution over possible y's. Let's say there's a Gaussian distribution. And then we could have gotten a different w, right? There's a whole distribution over here over possible w's. So what if this had been the w over here? Well, then we'd have a different distribution. So for every w, there is a probability of y prime given w, but there's a whole set of distribution. There's a whole distribution over w's. W is a random variable. And so we're integrating over all the possible w's that we might see to get this final posterior predictive distribution that's going to be a bit more spread out, because we're now considering all the possible w's that could have been producing, that have high probability under the training set. So this quantity is known, again, as a posterior predictive. And this is also illustrating a really key point, that in the world of Bayes, individual models don't exist, right? Like if you're truly Bayesian, you never think of the w. You always think of integrals over w. Like w is this unknown quantity, and whenever you need to actually do anything in the world, you integrate over w, because you don't know what it is, so you have to average. And so this, like if you take nothing away from this lecture, being Bayesian is about integrating over your parameters. So you never think about a specific parameter, you think about marginalized over parameters and then what's left over. Right. And then there's one last thing we can do, or we commonly do, and what we can do is we can compute something that's called the marginal likelihood. And the marginal likelihood is just the probability of your training set. Oops, not conditional. Probability of your training set. And this, again, is going to be an integral over all the possible w's that there might be. So we're going to have here probability of y given x. W, remember in our story, the x's are given, they're fixed, they're not coming from a distribution. If they were, we would need another, bit of integral there. But here, and then we have the probability of w. And this is useful. This is going to be the key quantity for model selection. We're going to get to that one though in a little bit. We're going to derive our way up to that. But these are our three, again, common quantities that we're going to be wanting to deal with when we do Bayesian methods and Bayesian methods for model selection. we're going to need
Bernoulli,
yes.
well, one thing that I think may be causing just a little confusion is in the probability of y prime conditioned on the parameters w and x prime, there's some confusion about why we don't need to carry the data around there anymore.
Great question. Yes. Okay. So our story, let's go back to our generative story. So our generative story says that once we have an input x and we sample a noise, all we need to produce the y, the new y, is w, x, and epsilon. So given this w, if someone tells us that here's the slope of the line, we don't need to know what the data points were that produced this, like where that slope came from, right? So down here, I could write this as integral over w probability of y prime w given x prime x y equal to integral over w probability of y prime given w x prime x y probability of w given prime this right here, and then this is just doing out the joint distribution and the chain rule. And then once I have this expression over here, I can look at things that are independent and so don't need to be considered. So when I'm computing the posterior on W, if I don't have a Y associated with this X prime, it's not going to affect my posterior, because for the posterior, I'm looking at, what was the input, what was the output. So this term does not need to be included here. It's a new point anyway. And then over here, going back again to our generative story, if I have W available to me, I know how to produce my Y. I don't need to know what these guys are. So there's some conditional independencies that are going on. Good question. Yeah, so when you're doing stuff with Bayesian methods, especially, I feel like most of your life ends up being kind of manipulating these sorts of probabilities, and it does get quite subtle. So these are good questions. Definitely, please keep them coming. Okay, so what I'd like to do is make this concrete. Actually, let's generally, okay. So let's start with this posterior over parameters. Let's just write out a little bit of really basic Bayes rule, and then we're going to go through this in a very concrete example, which hopefully will make everything make a lot more sense. All right, so if we just apply Bayes rule now, is different than being Bayesian in terms of like this marginalization philosophy. If we're trying to compute this posterior over here, then just by Bayes rule, this is equal to probability of y given x and w, probability of w given x, probability of y given x. That's just me applying Bayes rule. And now I'm going to do a couple of manipulations or a couple of simplifications here. First, I'm going to notice that this term over here, well, the prior doesn't depend on x, like the locations of x don't affect w. That's the assumption that I made. Again, it comes from my story, right? I could have had a story that that w was produced from something that depended on x, but my story is that w comes from its own prior distribution, and that there's no link like this, right? My story would be different if there was a link there, but there is no link in my story, and that's why I can down here remove the dependence on x and say this is just p of w. So a lot of times, at least for me, I find it really helpful to pin my math to the generative model, to the generative story, because that tells me what sort of independences, it specifies what things should be independent and what things should be dependent on each other. So here we go. And then the other piece that I'm going to note here is that this lower term is, does not involve W. It's just the marginal, the marginal probability of the Y's. So since it doesn't involve W, I can say that this is just proportional to P of Y given W, P of W. And the reason why I'm going to focus on the proportionality is that in cases where we have conjugacy, the proportionality will be easy to compute, or easy to deal with, right? So I'm going to emphasize this point because if there's settings where doing the Bayesian thing is very easy, that's when your models have conjugacy, and there are settings where it gets quite hairy, and those are the settings where you don't have conjugacy. We're going to go through an example now where things are conjugate. And one thing I want you to pay attention to is how we take advantage of that conjugacy, because in homework 3, problem 1, you're also going to be working through some of this math for a different model. And I and the staff highly encourage you to take advantage of conjugacy as you do this, because it's a lot less hairy if we take advantage of the fact that certain distributions are conjugate to each other. Let's make that concrete. Okay, so let's turning the Bayesian crank with a Bernoulli beta model. So that's what we're going to do. Actually, maybe this is a good time to take it. If we want to take a 2-minute break, this is probably the right time, because then the rest of the lecture, most of the rest of the lecture, we're going to be going through this derivation. So let's pause here for 2 minutes. If anyone has questions, you can ask questions. If you just want to take a little break, you can take a little break. So David, you're pointing out a good point about like, don't we want a posterior over the W's? So if we observe the X's, does that tell us anything about W's, right? Does it? I think that's a really good question, and something to think about if we go back to our model over here, that if we only see X's, will that help us determine what our W's are? And in this particular case, if we only see the X's, then that does not really provide us enough information to really pin down anything about the nature of the W's. It says that, well, I'm going to collect measurements from these patients, right? And I'll tell you all about them. Tell me, what do you think the slope of the line is going to be, for the measurements? And if you don't have any measurements, you can't do it. As soon as you start seeing pairs of Y, as soon as you start seeing pairs of the Y's and the X's, then you start to have enough information to pin down what the slope might be. Yes. And so let me see. I'm just looking at the. Yes. Okay, good. And there's a question about, does the same go for W and Y? And so W and Y are connected a bit differently, but if you don't see the X's, again, you don't have anything to use to start pinning down what the slope would be or could be. All right, So now let's try to make this very concrete with a very specific model. So we're going to just look at coin tosses. So the coin lands heads with probability theta in this particular case. X is the result of the toss. And we don't have a Y in this case. We're just going to work through we're going to be able to still work through the whole Bayesian reasoning, the whole crank with this very simple setting. Again, I'm trying to create as simple a setting as possible so we can go through it in lecture, but the same idea is going to hold if we had an X and a Y. So here we go. We have the probability. So what I just wrote down in words, the probability of X given theta. I can write this down in terms of mathematical expressions as theta to the X power 1 minus theta to the 1 minus X power. And this works because X is either 0 or 1. So I'm going to say that our tosses are 0 or 1. And if it comes up heads, then the probability was theta. If it comes up tails, then the probability was 1 minus theta. Now, if I have an entire data set, if I've done many tosses of my coin, so I have done n tosses, this, given theta, that's going to be equal to product over all of my n tosses, theta to the xn, 1 minus theta to the 1 minus xn. And here, just in terms of potential confusions, the ordering is going to, I'm working with a specific ordering, right? Like the first toss came up heads, the second toss came up tails, etc. So that's why for those of you who are used to putting like a binomial factor in front, I'm dropping that, and it's not really important to the discussion anyway. And if that made no sense to you, that's okay. The point here is that we're just going through every single coin flip, and we're just multiplying the probabilities of every single coin flip, which are independent given the theta, right? Once you know the probability that the coin comes up heads, we can just go through each particular flip and product out the probability that that flip came out in a particular way. And now I can write this down as theta. I'm going to use n1 as the number of times that the coin comes up heads. So that's the number of heads times 1 minus theta and 0, and that's the number of tails. Right. So far I've just basically established the setting that we're in and the basic math. Before we go any further, let's just take a note. So theta maximum likelihood, also known as theta MLE, maximum likelihood estimate, is going to be the theta that maximizes this probability up here. And I don't want to spend the time deriving this. If you haven't done it before, you can do it as an exercise to figure out, okay, what is the value of theta in terms of n1 and n0? You can take the log, move stuff, take derivatives, move stuff around. But what we will find is that the maximum likelihood estimate is equal to this very intuitive looking quantity. So at this point, if we weren't thinking that theta is a random variable, what we could do is we could say, all right, I got my 50 flips and there are 30 heads among those 50 flips. I think that my probability of heads should be 30 over 50 or 60%, right? That would be my maximum likelihood estimate. And I'm just going to note this as, one option or inference on theta, right? And we talked about this in a previous class. But that's not what we're going to be focused on today, right? Just remembering that this is one of our choices. All right. So now let's put a prior on theta. So our assumption is going to be that theta was drawn from some p of theta, which is going to be a beta distribution. I'm going to draw a picture and explain that in just a moment. And then after that, that was like our step 0. The next step is then we're going to draw n times x little n comes from a Bernoulli with probability theta, right? So this is our story. And this is our, the first part of our story is that we're putting a prior on the theta. And the prior that we're going to choose is that p of theta is equal to some constant, which I'm not going to worry about at the moment, theta to the alpha minus 1, 1 minus theta, theta minus 1. And why do I choose this particular form for this, this distribution? Well, it's going to turn out that it looks a lot like this form over here looks a lot like this form over here, and that's where we're going to get our conjugacy. But before we put the the prior and the data together, I just want to draw a couple pictures for you. For those of you who have maybe not seen a beta distribution before. So beta distribution is defined on 0, 1. And if we have alpha equals beta equals 1, it's just a uniform distribution between 0 and 1. So that would be if alpha and beta here were equal to 1, then you can even see this in the expression, right? That this is going to be theta to the 0, 1 minus theta to the 0, and p of theta is just going to be a constant. And so that's how we would end up with a uniform distribution between 0 and 1. And then when we have alpha and beta being less than 1, we're going to get distributions that look kind of like a U shape. So this is alpha, beta less than 1. I should use different colors. And when you have alpha and beta greater than 1, you're going to end up with distributions that look like this. So this is alpha and beta greater than 1. The exact picture is not super important, but what I want you to have in mind is that you can change. The prior is your subjective decision, right? So you're going to have to make a decision about if you're doing this sort of Bayesian approach, then one of the really big decisions is like, what is going to be the prior that you're going to put over the data? So it's important to know what it means. And one way to think about alpha and beta for this particular case is that you can think about my prior is that, I believe that I've seen 2 fake heads and 2 fake tails, right? So that would be alpha and beta equal to 2. Or I've seen, actually, I think I'm more skewed toward, my prior, when we're not seeing any data, I believe that heads are more likely. Like I imagine that, if I had 10 flips, 9 of them would be heads, right? And that would be equal to saying, or equivalent to saying that alpha is equal to 1, 9, sorry, beta is equal to 1. So there's a way in which you can think of alpha and beta as fake counts. And the bigger alpha and beta are, the more you think, more you're sure about what's in your head, the less you will care about the data. So let's make that concrete, working through a bit of math. So this is our prior. So now let us look at the probability of theta given the data set X. All of the data, let me just write it out this way so it's clear between capitals and lower cases. All right, so now we're trying to find the posterior distribution over theta, and that's going to be proportional to, using Bayes' rule, probability of x1 through xn given theta, probability of theta, and that was now equal to z alpha beta. Oh, I'm writing it in the opposite order. You know what? Just for clarity, let me write the likelihood first. Okay, so theta to n1, 1 minus theta to n0, that alpha beta. So I'm putting together these terms. And now we notice something kind of cool. So this is equal to, let's move this normalizing constant out front. theta to the n1 plus alpha minus 1 minus theta, and naught plus theta minus 1. So this is the expression that we get. And remember, this whole thing was proportional too. So what we have noticed is that we have something that looks like a new beta distribution. That as soon as I see this, I can interpret this new thing as a beta distribution. And so I can say that this posterior is now beta n1 plus alpha n naught plus beta, where the prior, so this is the posterior, and recall that the prior was beta alpha theta. And this is where the conjugate z comes in. Because the beta distribution and the Bernoulli distributions are conjugate to each other, I ended up with another beta distribution. And I didn't have to churn through all the math of what are the normalizing constants. And when you do homework 3, problem 1, don't churn through all the math of all the normalizing constants. You're going to be doing this with Gaussian distributions. But note that here our key statistics were the alpha and the beta. When you have conjugate distributions, what you end up having in your posterior is just an update to your conjugate distributions. You stay in the same family as your prior. Great. All right. Let me pause there briefly, see if there's any questions before continuing onward. Charo?
Yeah, so I was just curious if, like, for the sake of simplicity, we always just end up using conjugate prior and posterior distributions, or if there's ever a case where it makes more sense to like use distributions that aren't like as compatible.
Yeah, absolutely. So this is a important question. So in simple, or I think so you definitely don't always use things that are conjugate, but there's always this tension, not just here, but I feel like in general in machine learning, between creating something that you can compute and optimize and something that like really matches what you think is going on in the environment. So certainly like in our lab, we do a lot of work with deep models and we put priors over deep models, and none of that is conjugate. And honestly, none of it is even nicely. You can't use even approximate techniques also have issues, but it wouldn't be research if it was easy, right? But so I think you need to figure out what's the right sweet spot for your particular application. And at the end of the day, if you're being Bayesian, the thing that you probably care the most about is getting a good quality posterior predictive. That when you have a data point and you're trying to make a guess of what that data point is, you don't want to just you don't want to pin your hopes on one particular number. You want a distribution over potential numbers that you might get. And to the extent that that variance helps you make good decisions, right? That's to the extent that that variation can tell you that this is a case that I really should be careful because there's such a range of potential outputs that I should be more conservative in my choice versus I'm pretty sure I know what's going to happen. I'm going to optimize assuming that that will happen. That's the part that really ends up being important. And the term is often used like loss focused or prediction focused machine learning, where you kind of go backwards from your final goal and you're trying to figure out what quality of uncertainty estimation do you need. So yes, like there's always going to be this tension. Absolutely, you should start with stuff that's conjugate, and then when it doesn't work, then you go to more complicated methods. Okay, so let us look at a really simple example here. Suppose that alpha equals 1, and actually let's make it 2, and beta equals 2, And we've only done 2 flips. So we've seen 2 heads and 0 tails so far, right? So as we started out, we probably, I'm just drawing pictures. So our prior was going to look, it would have looked something like this up to 1. So this is saying that, hey, like, I think that the 0.5 is a bit more likely, but I only believe I've seen like, 4 fake counts in the past. Your posterior is going to be shifted. It's not going to be, again, this is just giving you like cartoon pictures. It's going to say, well, you've seen 2 heads, right? But you believe you've seen 2 fake tails, right? The beta are kind of like your fake tails. So you don't put all of your weight thinking that the probability of heads is going to be 1. Your distribution, this prior, is going to shift over a bit like this way. And the 2 things that have happened is shifted over, it's become a little more peaky because now you have some more data to start trying to reduce the variation in your posterior. Fake tails, sorry, right. So what I'm using when I say fake heads or fake tails, what I mean is like the values of the alpha and the beta. Like, one way to interpret the alpha and the beta in this context is to think, before you do any experiments, like, how many tails do you think you've already seen? If that's a helpful analogy for you, then run with it. If it's not a helpful analogy, don't run with it. Just, if the equations make more sense as equations, that's totally fine also. But I'm just including that interpretation, which is kind of becomes visible here, where we're adding the number of heads that we've seen to alpha and the number of tails that we've seen to beta, right? So there's a way in which, like, the units of beta can be thought of as the number of tails we've seen, and the units of alpha can be thought of as the number of heads that we've seen. All right. So this is what's going to happen in pictures. And one thing we can ask is that, what's this point, right? So this point has a special name. It's called the maximum a posteriori estimate. And it's also known as the MAP, the maximum a posteriori estimate. And again, I'm not going to go through all of the math of solving for this. So this point over here is going to be the maximum, it's going to be so the MAP will maximize this with respect to theta. So remember that the MLE was maximizing, so the MLE maximized this expression over here, which was just the probability of x given theta. And now the MAP is going to be maximizing the probability of the data given theta at times the prior. So we can do the same exact sort of math that we would have done with the MLE to get this expression. And we'll get theta MAP is equal to n1 plus alpha minus 1, n1 plus n naught theta minus 2. And if you look at this expression, it's exactly the same as the MLE expression, except we're kind of including the fact that we had this alpha minus 1 and beta minus 1, right? If we look at this expression over here that I said is the new beta distribution, it has exactly the same form as this over here. And so this expression over here, where it's n1 over n naught plus n1, those are these 2 terms over here. For the MAP, we're doing exactly the same thing, except now our terms look a little different. We have these in our exponents. And so here's our MAP expression, right? So here's the expression that we get. And now for our really simple example, we can compute what this would be. So like in our example, what do we end up with? Well, if we have n1 is equal to 2, and we have alpha equals to 2 minus 1, so that's a 3 up top. And then we have n1 plus n naught is 2 plus alpha plus beta is 4 minus 2, we get a fourth. So here we end up with 3/4 as this point over here. And remember that theta MLE in this example would have been 1, right? Because we've only seen heads. So it would jump to the conclusion that you will always see heads. So this is a convenient sort of quantity that we have so far, this map, right? But it is not truly Bayesian, right? Because as I said at the very beginning, Bayesians always integrate over their models. So we don't want a point estimate. We don't want to say that, oh, the theta is this thing, though that's maybe a reasonable starting point. What we really want to do is say that theta doesn't exist, right? Theta is a random variable. It's kind of silly to say that theta is equal to one thing or another thing when actually, well, we just computed there's this posterior distribution over over theta. So what we really should be thinking about is the posterior predictive. What we really, really care about is what's the probability of x, mu x, given x1, given xn. That is the quantity that is truly the quantity of interest. And that quantity of interest is going to be integral over theta, probability of x given theta, probability of theta given the data. Here again, I've done this separation where I'm assuming that every coin flip is independent given theta. So if I have probability of mu x given theta and data, I can drop the dependence on the data just like I did before. And then you have probability of theta given the data that you have already seen. So this is the thing that I truly am interested in, right? Like I'm about to flip a coin. What's the probability that that coin will come up heads? And to answer that question, I need to think about, well, given the data I have, there's actually a range of coins I might have. And I want to integrate over all the possible coins that I might have available to me. So if I go through this, now, so that part is general. Like so far, this math is general. Now I'm going to start subbing in things that are very specific to our Beta-Bernoulli example, right? I just want to highlight that fact. So you can't just do what I'm about to do is specific to this distribution. So what's the probability that of x coming up heads? Let's make this specific. Of x coming up heads given theta. So that's just theta, right? Again, this is very specific to the Bernoulli distribution, right? This would not necessarily be true for any distribution. It's true for the Bernoulli distribution. It allows me to write things out easily. So if I look at this, I can write this as the expectation over the posterior of theta, right? Again, this is specific to the Beta-Bernoulli case. And when I look up, I'm not going to go through, this is kind of the niceness of working with distributions that we know about. We can look up what is the mean of a beta distributed random variable given some distribution, and we'll get alpha plus n1, alpha plus beta plus n1 plus n naught. And in our example, this turns out to be alpha was 2 and 1 was 2, so this was 4. And then we had 6 on the bottom. This equals 2/3. So now I think it's useful for us to just look at these three quantities, these three ways of doing things. So the first way that we talked about was just MLE over here, right? It said find the theta that's the most likely theta given the data, and then use that to say when I flip a new coin, my coin will come up heads with the probability based on what we've seen with the data. Option 2 was the map. And the map said, let's put this prior, let's compute the the probability of theta under the prior, under the prior in the data. Let's get the posterior. And let's just pick the peak of the posterior. So when I ask the question, how likely is this coin to come up heads? My answer is the peak of the distribution. That's theta map. The final choice says, this is all silly. Don't pick a particular theta. Integrate over all the possible thetas that you might have. I mean, gee, you just calculated an entire posterior over theta. Why are you throwing it away to compute, this map value? Why are you choosing just the peak of this distribution when you have the full distribution? And so now we integrated over the theta choices. And when we did the integral, which in this case turned out to be easy because things were nice and conjugate and blah, 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 we get the number 2/3, right? Which is more spread out, right? Less likely, because if we flip up to my cartoon, there were times where you might get this map value, but when we're integrating, we're thinking of all the possible thetas that we might get, and we're averaging over all of those. I'm going to pause there to see if there's any questions. And then we have one more thing to do before going into our concept check. Okay, Raphael?
So they still assume that we had a prior on theta, right? Even when we did P of x given x1, xn.
Yes, so we do have the prior. So the place where the prior came in is in computing this part over here. So this posterior is proportional to P of theta, P of x1, xn given theta. And yes, so just to confirm, the MLE was based only on the data. That's right.
Thank you.
Yeah. Okay. There's also a question of using the beta binomial conjugacy for generating y's. Given x's, that gets a little tricky. So there's an entire set of like generalized linear models that one might use in that particular case. I find that it's easiest to, once we think about y's, I think it's easiest to think about continuous variables, actually. And so in your homework, you're going to be dealing with a case where you're doing linear regression with Gaussians. So now you're going to put a Gaussian prior on the W's. All right. Great. So let me move on to one last step. So one more calculation. So remember, at the beginning, I said there were three things, right, that we would be interested in doing: the posterior predictive. Now, finally, we're getting to the marginal likelihood. All right. So what we want to do now is we want to compute just the probability of x1 through xn. And that's going to be equal to the probability, or like integral over theta, probability of these guys, given theta, P of theta, and let me do some substitution now. So the probability of the data is just equal to theta to the n1, 1 minus theta to the n0. And then we have our normalizing constant, theta to the alpha minus 1, 1 minus theta to the beta minus 1. So that's the integral that we're trying to solve. Let me pull out from this integral this initial normalizing constant, and then combine terms inside the integral. And now that I'm here, I'm going to make an observation. I'm going to say, hey, this thing looks very much like a beta distribution, right? That's the conjugacy that we had noticed before as well. But what's missing in terms of making it a distribution is that normalizing constant. So what I'm going to do is I'm going to multiply and divide by this new normalizing constant. So this would have to be the normalizing constant n1 plus alpha n0 plus beta. there's this new constant that goes with this new distribution, right? It looks like a beta, except we're just missing this constant. Plus alpha, sorry, talking and writing at the same time, great. Okay, and now I'm going to pull out one of these. These are just constants, right? I put it inside the integral, but I don't need to keep it inside the integral. And finally, I'm going to make the following observation. Oops, N1. And the observation I'm going to make is that this last integral is just an integral over the distribution, right? And if you take an integral over the distribution, so this is just, you know, beta n1 plus alpha and not plus beta, you're just going to get 1, right? If I take the integral over all possible values of, you know, out of a Gaussian, etc., you know, I'm just going to get a 1. So this whole thing is going to be 1. And this is going to be my P of x1 through xn. Why do I care, right? So the reason that I care this gets to finally the thing that, you know, we were ostensibly talking about today, which is model selection. So suppose that I had a couple of different choices for this model. So suppose I had 2 choices of, you know, alpha 1, beta 1, or alpha 2, beta 2 as possibilities for where my theta came from, right? I'm not sure where my theta comes from. Like, what's the right model, right? I had to make up some prior distribution. So if I wanted to compare, I can compute P of x1 through xn given alpha 1, beta 1. So notice now I'm integrating over the thetas, right? And here I can compute probability of x1 through xn given alpha 2, beta 2. And I can see which class of models is the more likely class of models. And that's because remember, Bayesians never care about a specific value. We're always going to be integrating over theta. So we never need to pick a good theta, but we do need to pick a good class of models. Like, should we be thinking about lines? Should we be thinking about parabolas or quadratics? Should we be thinking of cubics? Those are model classes, right? And what the marginal likelihood lets you do is compute the probability over a class of models. And basically what you're going to end up with is this Goldilocks phenomenon that now I'm going to simplify because and move away from conjugacy, because the idea is a little easier to explain with in pictures or in ideas. You know, suppose you know, we have classes that look like theta is an element of 0.1, theta is an element of 0.1, and theta is an element of 0.2. What we will find is that this might not explain the data. Because it's kind of limited to, you know, this 0.1, we already saw 2 heads, right? Doesn't do very well in terms of explaining the data. This one might be just right in this example. And this one has too many options, right? It spreads out. It says that, hey, what if theta was equal to 1.5? But that's not possible, right? Because we know that this is a coin flip. So you're kind of wasting your probability mass by putting stuff out in a situation where you know it can't happen. So this is, again, in a crux, like how Bayesian model selection works, that You choose some class of models. And so the class of models, let me make this a little more explicit. You say that my prior is my class over model. So I have this prior versus that prior. And then once you have the priors, you turn your crank, you find out your marginal likelihood, and you do model selection. All right, I'm going to stop there and take questions. And then after that, we'll do a concept check that is going to look at this in particular. No questions? Okay, let's jump into the concept check then. So let me pull it up and share. So here's a link going to the concept check. Okay. Let me share. All right. So here's our concept check that we're going to be looking at. So in this concept check, you have two data points, 0, 0, and 1, 1. We're going to assume the following model. And importantly, to make this whole thing work out nicely, we're going to assume that the noise is basically 0. So we are in a situation where the y hat is essentially equal to a0 plus a1x plus a2x squared. Okay, that's just to simplify things so you can do all of this math, in a few lines on a scratch sheet of paper rather than having to churn through ugly stuff. So the first question is just implying like how will you fit the line, and then what you're going to be doing is you're going to be trying to solve for a0 and a2. And what we're going to do is compute the posterior predictive under this model with this particular distribution. And then you're going to think about what if it was just a line instead. So we're going to have two model classes here that we're thinking about. It's a parabola. And then the last question is going to ask you to think about what if you're fitting a line instead. So this concept check, you are going to have to work through like a few lines of scratch on paper or somewhere, most likely. But just a hint in advance, like it should not get messy, right? If it gets messy, then you're making it probably more complicated than it needs to be. Take a step back, think about what's the core idea here, and then hopefully it will be less messy. All right, so let's go ahead, stop the share, and split into breakout rooms. Sorry. All right, so that was, and sorry about the weird issue. It seemed like it opened, but didn't quite open. So people had a bit less time. If you didn't have time to get too far, that's okay. I'll go over the basic steps now. And then also, this is a type of problem that I encourage folks, if you didn't get time to go through the whole thing, which is totally understandable, try to do it yourself afterwards, because it just is, it's a good exercise. It's a simple exercise for this idea. And then you'll get to reinforce it again during homework treat. But it's nice to work out an example that you can just do on pen and paper with very few actual calculations. All right, so question A is just asking if the noise is approximately 0, what does this imply? So it implies that the lines are going to go through the points, right? We don't need to consider that there's a bit of wiggle here or there. The lines go through the points. And that, assuming that the lines go through the points, let us start to solve for specific cases with by just subbing in variables. And actually, I'm going to stop my share screen and instead switch back over to whiteboard because I think it's easier to do there. So let's do this. All right, here we go. So we had our 2 data points, and we had a0 plus a1x plus a2x squared. This was 0, 0. This was 1, 1. And so now we can start solving. We can say 0, y is equal to a0 plus a1 times 0 plus a2 times 0. That's by plugging in this point over here. And so we get a0 is equal to 0. Right, that's just fixed. And then for the 1, 1, we get 1 is equal to a0, which is 0, plus a1 times 1 plus a2 times 1 squared, right? So all I'm doing, if I had this equation over here, is subbing in for values, right? There's 2 data points. And so what I get here is that a2 is equal to 1 minus a1, right? So here we have this guy and we have this one. So now let's suppose that a1 is in -1, 1, and a2 is big, right? So in the problem we had like this -100. Did we say 100? Did we say 200? I forget. Okay. We said -100. Okay, great. So the point is that this doesn't matter, right? Because there's so many values of a2, but we know that a2 is constrained by being 1 minus a1, and a1 has to be between -1 and 1 uniformly. So if a1 is equal to -1, right, a2 is going to be equal to 2. And if a1 is equal, by the way, I realize we're going over time. I'm going to quickly finish this up for folks who can stay for this part. If a1 is equal to 1, then we're going to get a2 is equal to 0. So at x equals 1/2, right? What's the range of values? So we have a0, which is 0, plus we could have been in a situation where a1 is -1, 1/2, plus a2, which is 2, times 1/4. So this is -1/2 plus 1/2 equals 0. Oh my, these numbers are not made up to work out cleanly at all, are they? It's clearly very designed. And now, so this is the a1 equals -1. Here's the case where a1 is equal to 1. 0 times 1/4. Oh my, beautiful again. So here we go. So what do we get if we're trying to make a prediction here? So we know that over here, these points are observed, right? There's no uncertainty in the prediction. But when we're trying to make a prediction here, we're not sure, right? Because there's things that look kind of like a line, and then there's many parabolas that could be going through. And so we have this uniform distribution between y equals 0 and y equals 1/2. And this thing over here is our posterior predictive over y at x equals 1/2. And in the case that it was a line, there would be no uncertainty left over. So the posterior predictive would just be the 1 point. But again, hopefully this makes sense. This makes this idea concrete. And if you think you still need a little bit of time to work through it, then please, like, this is a good concept check to kind of work on separately and see if you can get to this same conclusion. All right, so I'll stop now and stop the recording.